All right. First of all, a little bit of review of things we've already done. This will be the third time some of you've heard this. Our immune system's in two main parts, non-specific and specific. The non-specific is also called the innate. Where else in biology do we use that word innate? When you talk about innate behavior, what does that mean? It's like built in, like programming, like instinctual kinds of stuff. Instincts. Innate. Built-in stuff. Your skin is the main part of your non-specific immune system. Waiting on everybody to focus here. Obviously, it's a barrier, but it also puts out acidic secretions, antibacterial secretions. Inflammation is really important. When your cells in your connective tissues called mast cells get damaged, they send out this SOS chemical, group of chemicals actually, mostly histamine, but also prostaglandins, and those make more blood come to an area and make it swell. That brings with it white blood cells, it brings with it platelets to help clot, helps your immune system. And these other things are also all part of your non-specific immune system. Interferon. What does interferon interfere with? Virus what? Which is called? Lytic cycle. The lytic cycle. Alright. Also remember the normal flora. Flora usually refers to what? Usually plants in a place. Okay? And what's the word for animals in a place? Flora and fauna. Okay? But here, you don't have any plants growing in you, I hope. But you have some bacteria living in your intestines, living over your skin. And mostly what those things do is they crowd out other things. They block them. They're like your blockers. They keep those things from growing there. You also have phagocytes, which sort of just eat random things like viruses and bacteria. Your saliva and your tears have this chemical in there called lysozyme, which breaks things down, germs mostly. Your mucous membranes help to filter out stuff. They also help to warm up the air and moisten it. I asked you a question on that worksheet that you just turned in. 3 things mucous membranes do. They filter, warm, and moisten the air. And then the pyrogens are things that cause fever. But what I want to concentrate on today, pretty much the whole time, is the specific part of your immune system. And sometimes it's called required, because you have to build it up, you have to get it. You have to go get specific immune system. And 2 key words, antigen and antibody, you got to know those words. What is an antigen? It's a foreign protein. When you get antigens in your body, foreign proteins, in response to antigens, your body makes what? Antibodies. And those antibodies are like smart bombs. They'll go out and they'll attack the antigens, and we'll talk about how they do that. They're made very specifically for those antigens. All right, the first part of the specific immune system we're going to cover, there's really 2 parts to the specific immune system. The first part is antibody-mediated immunity, sometimes called humoral. It's called that. What were humors back like to the Greeks? The Greeks talking about the humors. What are they talking about? Talking about different kinds of fluids. It turns out these antibodies can only kill germs that are in your body fluids, not where. If they've already got into your cells, antibodies can't get to them. So these can only get germs that are outside your cells. That's an important point to know. Antibodies can't get germs that are already in your cell, like a virus. If it's already in, it can't get to that. It can only get it while it's in the blood or in the body fluids. Can't get to it inside a cell. That's why it's sometimes called humoral. But with this antibody-mediated immunity, usually the first thing that happens is some kind of phagocyte, like a macrophage, will ingest, phagocytize that germ, and then break it up. What do we call that process? Phagocytize it and break it up. What's that called? You use lysosomes to break it up. What's it called? What kind of digestion? Intracellular digestion. So the germ gets intracellularly digested. And then after it gets digested, the macrophage will take pieces of it, and those pieces of it, it will present. It'll do what's called antigen presentation. It will take those pieces and stick it up on the outside of its cell membrane. On a complex, a flagpole that I've been calling them, called the MHC class 2. This is the way cells communicate. It's holding up this germ and saying, look what I killed. Think of it sort of like a trophy hunt. Here it is. I found this is in this, it's dangerous. It's communicating that to other cells. And there are other cells that will dock with that MHC class 2, and that docking process will activate them. And the main cell that's going to dock with that macrophage is called a helper T cell. But this works a lot like enzymes and acrocytes and substrates. Only certain helper T cells can fit to that antigen. It's very specific. Once one comes in that can fit, the macrophage is going to release chemicals called interleukins, signals, cell signals, signals between what? What kind of cells? What does leuk mean? White. Signals between white blood cells. And that's going to cause that helper T cell to start to clone itself. The one that'll fit, the specific one that'll fit will start to clone itself. Once it does, it's going to go out, and it's going to start to look for B cells, another kind of white blood cell, B lymphocytes. Those B cells also phagocytize that same germ and display its antigen on their cell surface. These helper T cells have been turned on by the macrophage. They know what they're looking for. They go out and they'll dock with that B cell, and they'll release other chemicals called interleukin-2s that will turn on not only more of themselves, but also these B cells. The cool thing about B cells is they can do two things. Most of the B cells, once the right one is found, the one with that right fit, most of them are going to turn into what are called plasma cells. And plasma cells are basically factories for what? Antibodies. Most of the B cells turn into plasma cells, and they start chugging out antibodies by the thousands, very, very fast. Antibodies specifically made for what? That germ, whatever that germ is, and only that germ. Some of the B cells, though, don't turn into plasma cells. They hang around as what? Memory B cells. Which means the next time you get that infection, they can respond really, really fast. Some of the helper T cells also hang around as memory helper T cells. So as you experience more germs, you acquire more immune system memory. That's why it's called what part of your immune system? The acquired immunity, because you get it over time. So what you need to realize is that some kind of macrophage eats the germ, presents its antigens on its surface. A T cell with a specific receptor, one that'll fit, like an enzyme and a substrate, lock and key kind of fit, will come in and bind to that. When it binds, it gets activated by interleukins. It will then go out, after it's cloned itself, find a B cell with that same antigen, a B cell that's killed that germ and held it up. They'll dock again. The helper T cell will turn on that B cell and tell it to make antibodies. Most of the B cells turn into plasma cells. Some hang around as memory cells for later. Now, a couple of things that we talked about. The receptor on the B lymphocyte has to be very specific for that antigen. If it doesn't have the right receptor, it's not any good. So alternative DNA splicing helps us to make all these different receptors that we have, up to 1 million different B cell receptors. But we only have a few genes for this. You only have a few genes for making B cell receptors. How can a few genes make 1 million different receptors? The whole splicing thing, right? Take out introns, put together exons. Take out different ones. And different times, different things are introns and different things are exons. We do get memory cells, both memory T and memory B cells, but a lot of those B cells become plasma cells, and they start chugging out those antibodies. The antibodies work in a couple of ways. One thing they can do is they can cause agglutination, which means what? They clot it up. They can bind to the germ and cause them to clump up. And we said to think of an antibody sort of like a handle. That if Megan here was a germ, and this is the antibody for Megan right here. Go ahead and grab one of that, Megan. Megan has now been marked. That antibody is like a mark for death. And it tells other white blood cells, hey, this thing's bad right here. You got to get it. And one thing you can do is that other white blood cells will come grab the handle. They'll grab the handle and they're going to escort her where? To the urinary system and get her flushed out. Okay? That's one thing. Another thing, this might be like a beacon sticking on her saying, you know, danger, 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 danger. And what's going to come around and kill her? A macrophage basically will come in and phagocytize and destroy it. So it could be a mark for death, here it is, come kill it. Or it could be, here it is, grab onto this handle and take them and flush them out kind of thing. So there's a lot of different processes that can work. But the key thing is that once you had an infection and you've successfully destroyed it, you've got memory helper T cells, you've got memory B cells, and we're going to talk in a minute. You also have another kind of cell called a killer T cell that you have memory cells of. All those cells, the next time you get it, respond so fast that you never get wet. You never get symptoms. The first time you get something, what do you think that might be? What's the word we use a lot for the first time? Primary. Okay? So the primary infection takes a while for your immune system to respond. It's kind of slow. We'll come back to primary. The secondary response, very fast. You make antibodies really, really quick. So quick you don't get any symptoms at all, typically. All right, we're going to watch this clip again. I know we've seen it a couple times, but we're going to watch it again just to make sure that you understand what's going on. Oops. All right, I want to touch on these MHC class II glycoproteins. We said to think of these like flagpoles on the outside of white blood cells. Phagocytes have MHC class II glycoproteins. After they've taken in a germ, intracellularly digested it, they take antigens from that germ and fly them up on this flagpole. It's a way to signal to other white blood cells, most of the time to your helper T cells, hey, this is out there. It's dangerous. Look for it. We've got to respond to it. It's on white blood cells. It's on phagocytes, macrophages, B lymphocytes, and other kinds of cells in your body that will phagocytize germs. And one other term that you need to know, this MHC class II, it's made to dock with a receptor on the helper T cell. That receptor on the helper T cell is called the CD4 receptor. We saw in that video how the helper T cell had a receptor that would come in and bind with the MHC class II. That receptor on the helper T cell is called the CD4 receptor. Once those dock, once the CD4 receptor on the helper T cell and the MHC class II on the phagocyte dock, that triggers the rest of your immune response. So it's pretty important. We know HIV wipes out helper T cells, right? That means you don't have any antibodies when you have HIV. It also, helper T cells are also important in the next part of the immune system, the cell-mediated immune response. So pretty much, once you get HIV, what you're left with is your skin. That's your immune system, pretty much, once you get HIV. So you're not left with a whole lot. Make sure you know that MHC class IIs are glycoproteins found on phagocytes. And they're involved in what's called antigen presentation. Taking a germ, displaying it on the surface of the cell. Before we go any further, just a little bit about an antibody. Antibodies are proteins. They're proteins made to attack a specific germ. They look like this. They've got chains. They've got what's called heavy chains and light chains. What do you think these little black lines represent? Bonds. What kind of bonds hold polypeptides together? Yeah, hydrogen and disulfide. These are disulfide bonds, which means some of the amino acids in here have to have what in them? Sulfur. Okay, sulfur in the R groups. This part down here is called the constant region. And a lot of times with antibodies, this is the part that acts like a handle. This is the part that other white blood cells can grab onto and escort those germs to where? Urinary system. This part up here is more like the active site. This is the part, it's called the variable region, that is made to fit a specific germ. It'll only fit a specific germ. So this is the part that has to fit. And again, it's called the variable region or sometimes the antigen binding site. One other term, sometimes you'll see antibodies abbreviated, IG something, like IgA, IgG. Another word for an antibody, let me just write it up here, is this big, scary sounding word, immunoglobulin. If you see that word, just realize it's another word for an antibody, immunoglobulin. And sometimes it's abbreviated IG, and there are different kinds of antibodies like IgG, IgA. Just realize if you see that big word, immunoglobulin, it's just an antibody. Just an antibody. So, back to what we were saying here, antibodies are proteins made to attach to specific antigens. They may act like tongs that white blood cells use to safely grab and transport pathogens. The antigen binding site is different for every antibody. And the constant region acts like a handle. It's the same in all antibodies. And remember that the different antibodies are created by alternative DNA splicing. That's why we can make so many different kinds of antibodies, because we have introns and exons. Would bacteria be good at making antibodies? You know, because they don't have what? They don't have introns or exons. Well, they don't have an immune system either. But they don't have introns or exons, so they couldn't do this alternative splicing thing that we do. All right, we want to talk about the other part of the immune system. This is something we haven't talked about at all yet. It's called cell-mediated immunity. This is the other kind of specific immune system response. Key point. This is very important that you get. Antibody-mediated immunity can only get to germs found where? In the body fluids, in the blood, in the lymph, the fluids between your cells. It can't get to germs that have already made it into your cells. What do we know? What kind of germ likes to get into your cells? Viruses, right? And while they're in your cells, what are they doing? They're replicating. So you need to kill that cell. You need to kill your own cells before what? Before those viruses all bust out and they lyse that cell and spread. That's what cell-mediated immunity does. Cell-mediated immunity, its job is to destroy your cells that have an infection before they can spread that infection. So make sure you get that point. Cell-mediated immunity's job is to kill your cells that are infected with some kind of intracellular infection. Most of the time it's a virus, but it can be bacteria. The main kind of cell involved in cell-mediated immunity is a cytotoxic T cell. Oftentimes it's called a killer T cell. Cytotoxic or killer T cell. The main cell involved in this process. These cytotoxic T cells have proteins in them called perforins. Perforin sounds a lot like what? Perforate. Perforate. Pokes holes in the cell membranes of these cells. It's like kind of like Wolverine, okay, the X-Man. Pokes holes in things and the guts of the cell just leaks out and it dies. So it kills infected cells. Helper T cells are also involved here. You got a lot of kinds of T cells. Something that I want you to make sure you know. The T cells are called T cells because they develop. They're made in your bone marrow where all your other blood cells are made, right? But the T cells are basically trained, they mature in a little gland right here in your chest called the thymus. That's why they're called T cells. thymus-derived cells. I want you to think of the thymus gland. What do you call those places where a ninja trains at? A dojo. They're like the dojo for T cells. Okay? Think of a thymus gland like a dojo for T cells. It's where they train. It's where they learn to fight. It's where they learn to kill the germs. Turns out, in a young child, thymus gland is pretty big. But in me, it's shriveled up to almost nothing. How come? Because I got my ninjas already. Okay, my ninjas are trained. Okay, they're ready to go. Okay, a child and ninjas are still in training. Okay, my ninjas are ready to go. Very important point, and we've talked about this without using this term before. Every cell in your body has an MHC called an MHC number 1, class 1 MHC. Every cell in your body has it. And these are basically how am I doing kind of protein. Remember that what your cells are constantly doing, if you remember when we talked about cell signal, we talked about this, that your cells are constantly breaking down proteins inside themselves and sending pieces of those proteins out on that MHC class 1. And it's basically like a check. So let's say that, everybody hold up your hand. We'll do the same kind of deal we did when we did cell signal. This is your MHC class 1 you're holding up. I am a cytotoxic T cell. I'm coming around. And I'm shaking hands with it. So Megan, she's okay. Caitlin's okay. She's okay. Micah, something weird going on with Micah. Okay? So when I find a weird little protein, on Micah's MHC class 1, what does that signal me to do? That signal me to kill him. Okay? So I pull out my Wolverine claws, my perforin, and I poke him with it, and out comes his guts, and I kill him because he's infected. He's got a germ inside him. Probably what kind of germ? Virus. Probably a virus. So the MHC class 1 is found on every cell, and the cell is taking proteins from inside itself and holding them up there. If you have a virus inside your cell, some of the proteins on that MHC are going to be virus proteins, right? So it's a way to signal, hey, this is in me. You need to come get me. Because if you don't, what am I going to do to everybody else? I'm going to infect them.
That's what a class 1.
Hold that thought. That's a class 1, yes. Hey. I hadn't seen you here this morning. Sorry. Yep. So an MHC class 1 is found on every cell. And it's a way to signal how you're doing. Yeah, I'm okay. No, I'm not. Okay, that's what it's for. But remember, every cell has it. So that's what an MHC class 1 looks like. We're going to listen to this video clip, and it's going to talk about cell-mediated immunity. Let me turn this off real quick.